G'day, I'm Dr. Kev, and up until now in Project 171, I've been using a CAD model as a little bit of a sketch pad to explore ideas as to what the car might be once it's created. But this model has got a little bit messy, so in this video I'm going to explore laying a foundation for a much more organised CAD model that should allow me to work more efficiently on this project. Welcome to Car Design Workshop. Now, when designing a car, we'll use many different computer-aided design tools. A good 3D model of the car will help us in a variety of ways. The most obvious of these is that we get to see the car digitally well before we aim to build it. This can help identify different geometries, clearances in the cars, and all sorts of details, how the assembly is going to work together. Now that's particularly useful if we're creating videos of this process because we can use it to create a lot of visuals. And really that's been one of the parts I've used the original model for. Beyond that, we're going to use the CAD model to create manufacturing drawings. And a big part of this is being able to communicate the manufacturing intent with other people that will be working in the project. And good CAD models facilitate collaboration between different groups, so sending out your models to different manufacturers or to other people that might be helping with some of the simulation. We can use the CAD models to enhance our simulation. We can use it for things like creating a suspension kinematics model, as well as things like our aerodynamic analysis and stress analysis of components. Structural analysis using FEA will be one of the main ways we're able to determine whether components are going to work or not in their intended installation. And our aerodynamic analysis using CFD will give us some insight into the performance of the vehicle at speed in a way that we're just not going to have the resources to do in a wind tunnel or with significant on-track testing. Another advantage of a CAD model is if it's been set up well, we can use it as a modular model where we can swap parts in and out as we're doing the design. And once all is said and done, this is a very useful, comprehensive record of the car's design, which is valuable for documentation as well as the compliance to various regulations we're going to need to do to register this car when it's finished. A lot of the CAD packages out there include a number of different computer-aided design tools, and choosing the right software can really have a big impact on the project. There are software that's readily available and freely available that is well suited to creating geometries. And if we were just concerned with things like the visuals, a software like Blender might be particularly useful. When it comes to the bodywork and creating accurate NURB surfaces, we might want to use something like a high-end surfacing software like CATIA or a cheaper, more readily available one like Rhino 3D. There are also a variety of CAD packages used to create parts and assemblies, and they have a variety of costs and capabilities. This would be software like Solid Edge, Autodesk Inventor, Fusion 360 or SolidWorks. And what we want in this software is something that's relatively low cost, easy to use, and has good capabilities and features. Finding a package that meets all of these at the same time is very difficult to find. Usually if we find something that's easy to use and has good capabilities, it's going to cost us a little bit. Now for this particular project, I also have a few things that I would really want from the software that I'm using. One, that I want it to be a parametric design tool. So something that is dimension driven and you can change those dimensions quite easily and produce new geometries from those. This is particularly important when we're looking at things like the suspension system and various components where we might want to move them and create lots of different iterations. Needless to say, we also want something that's got high level of accuracy in the dimensions. We want a CAD model that's going to closely resemble our manufactured items. I'm also going to want software that's able to import and export from common file types. Not always going to be able to work with people and manufacturers that are going to be able to use the files straight from the software I'm using. Now another more, personal desire for software is that I'm not a huge fan of cloud-based CAD packages. I want to be able to control the file storage and make sure that I have a copy of all of the files and they're not going to be readily available to other people. I want to have a level of control there. So I'll be looking for something that has local storage of data. And lastly, one of the things that's really important is I can't afford to spend a huge amount of time learning new software. While most CAD software can be used to do this project, often the best choice is going to be the choice that you're already using, where you've already invested the time to learn the software. Now, I've spent a fair bit of time with a number of these packages, but probably the bulk of my time has gone into Solid Edge, Autodesk Inventor, and SolidWorks. And the one that I use most often is SolidWorks. It's not a perfect package. There's a number of things in it that can make me quite frustrated at times, but it's a really powerful package and more than capable of doing the work required for this design. Now, regardless of the CAD package that I'm going to use, it's really important to create an organized CAD model. This will help reduce the number of mistakes that I'm likely to make, improve efficiency, and make it easy to work on different parts of the project. Now, this is going to be a fairly long project, and sometimes I'm not going to be in the model for quite a while. So I need to make sure that I can go back into the model, open it up, and create productive work, even if I haven't been using it for a while. So this means having a good plan of the CAD model and some organization around that model to make sure that I can easily get to what I need to get to. Now, this includes establishing a file management system to make sure my files are organized on a hard drive. I do use cloud storage for most of my projects so that I can make sure that I've got local copies in a variety of different places and I can access my files quite easily. But it's important that the naming conventions of files and folder structures and version control is well managed so that I'm not creating a lot of duplicates of files or unnecessarily repeating the amount of work that I have to do. Also, because I'm using this CAD package for a variety of different things, from the visual creation of the model through to manufacturing drawings and simulation, I need to make sure that I'm planning what modeling technique is going to be used for different models and what sort of accuracy and precision is needed for each model. For example, if I was to use a model for CFD, I wouldn't want to be including all of the internal detail there. And in order to create a reasonable mesh, I'd probably want a de-featured model. So it's very likely that I will need to have a separate CFD model than the main manufacturing model. When it comes to parts that are purchased, don't need to create all of the details, but I do need to make sure that any of the mounting faces are created quite accurately, and that at least the overall geometry and overall size is captured so that you don't run into any problems when it comes to maintenance of the vehicle. Now, this organization alone is a lot of work. When I've worked in design offices, you'll have a CAD manager or drawing manager to take care of a lot of these issues. Now, I need to make sure that any of the organization that I'm using is quite light, because I don't want to be spending all of my time organizing things and none of that time creating the objects. Now, one of the most important things to consider very early on when it comes to your conventions, naming conventions, is a part numbering system. And a part numbering system, when applied appropriately, can end up being your file names. Now, there are a few schools of thought on what you do here. You can just create a file name that is descriptive of the object. Now, this is a real problem once we start to get to any serious complexity in a CAD model. If we're looking at a car CAD model, you're going to have a lot of different brackets, for instance, and it doesn't benefit anybody by just naming them bracket A or bracket B. And you'll often end up with really long convoluted names such as front upper fore suspension bracket. Now, this is really good if you're going to look at the part and wonder what is that part, and the part name will give you that clear description. But these names get unwieldy and difficult to use over time and can for a really complicated assembly really slow down your time. Now, the other approach is to create a part numbering system where you really just have a serial number applied to each part. Now here, the file name is going to be less descriptive of the overall part, and you'll often need to compare that to a drawing register or a part register in order to determine what that part actually is. But for a complicated assembly, this is almost certainly the best way. Now, if I was to look at an example of, say, the Lotus Elise service manual, it'll give you a run through of the part numbering system that Lotus would use for these Elise range. It starts with a version or a modification of the part, and then it has a 3-digit number that's used to identify what vehicle the part is from. And then there's a series of functional groups. So these are functional groups where they break the car up into different sections. So chassis, body, front suspension, rear suspension, and so on. After that, you have a serial number, which allows there to be up to, say, 10,000 parts in that functional group for a given car, which is more than enough. And then it ends with a supply route, which is for internal use. So at a glance, if you were working at Lotus, you would very easily from this be able to see at the very least what vehicle it's assigned to and what functional group it is. Now, I've experienced a similar kind of system to this when we were working in Formula SAE or Formula Student. When we got the cost report, we have the same sort of idea, this functional group, except in that case, the functional group has a couple of letters. So we might have a chassis, which is CH, or steering, which is ST. So rather than reinvent or create a completely new system, I'm going to borrow heavily from this Elise numbering system, or the Lotus numbering system, but instead I'm going to apply a 2-letter code to the functional group. I'm also going to put a revision at the end of the part numbering system and a company designator at the beginning. So the way the part numbers are going to go is I'm going to have a company designator. In this case, it'll be H for my surname. A product number for this project, it'll be 171. And then there's going to be an area code. So I've got AA for standard fixings. This is going to be everything such as bolts and hose clips and things that are used in more than one area. Now, one advantage of collecting all of the bolts into one area rather than having them spread amongst the suspension and powertrain and so on is it can help you standardize the sizings of bolts. I don't really want to use different size bolts in the powertrain than I use in the interior. I want to try and reduce the number of different bolt sizes that we have. And then we have bodywork, brakes, chassis, cooling, electrical, engine, exhaust, fuel system. Then we have heating, ventilation, and air conditioning. Not entirely sure what we're going to be doing in that space in this car, but it's good to lay that out as a separate area to start with. Then interior, steering, suspension, transmission, and wheels and tires. I'm also going to create 2 other categories, an unassigned area code. Now this is going to be useful for when I'm bringing a part in. I'm not entirely sure which area it's going to be in, but I want to create the model to start with. And then another one for temporary. And this allows me to still use the model as a sketch pad for ideas, but making sure that I can identify which of these parts I don't want to be in the final model. And just like the Lotus version, I'm going to then have a part number identifier, which will just be 4 digits, and then a revision. Now I'm going to put another area code in here that I'll call a GA, and that's going to be for my general arrangement models. So these are the assemblies that are going to really take parts from a number of different places and are really just our more top level assemblies. For each of these areas, I have created a drawing register that collects the information about each of these files. It provides a short description at the start so that we can link a description to the file name, but also includes details such as suppliers, the number of these parts we're going to use, the cost, the weight, and so on. Now I'm doing this in a spreadsheet. I'm sure that this would probably be better done in a custom database or something like that, but I don't have a huge amount of experience with databases and I don't really want to start now. It will mean that spreadsheets can get a little bit difficult to use once they become quite large, but that's a trade-off I'm willing to take. Another thing that I need to consider with the model is what sort of coordinate system I'm going to be using and what origin am I going to be defining for the vehicle. This is particularly important because I'll be using the CAD model data for things like our suspension simulation and some of our vehicle dynamics calculations. So I'm going to be transferring numbers from the CAD model straight into other pieces of software and other calculation tools. And if I'm iterating a lot and the CAD model's sort of X, Y, Z coordinates are different than what I'm using in another package, that can be a very frustrating experience. If we were to look at the Society of Automotive Engineers and we were looking at calculations for that, the SAE coordinate system would say that X would be pointing forward, Y would be to the right, and Z would be pointing downwards. And this is a system that's widely used in the automotive industry in the US in particular, for calculations. There are some advantages to doing it this way, but I'm going to be using an ISO coordinate system instead. And this has our X coordinate system pointing forward, our Y's to the left of the vehicle, and our Z in the upwards direction. And this is commonly used in international standards. We also want to think, where do we put the origin of the vehicle? Now, one place we could consider is having our origin at the center of gravity of the vehicle, and that can be useful for vehicle dynamics calculations. But we're really not going to know where that center of gravity is on the vehicle, so it's very difficult to start building a model around that. For the Y coordinate, it definitely makes sense to have the origin placed along the center line of the car. In a two-seater car, there will be a driver side and a passenger side, so there is a lack of symmetry there. But when it comes to the general chassis and suspension and so on, cars built for the road are largely symmetrical, so it makes sense to put that origin along the center line of the car. For the Z-axis, it makes sense to have the origin at the ground. So the only real question is, where do we put that 0 point for the X coordinate? We could put that at the center of gravity, but again, we don't know where that's likely to be. The other most common places to put it would be at the center of the front axle or at the center of the rear axle. Now, I'll generally put the coordinate system at the center of the rear axle, and the main reason for that is when the front wheels steer, their contact patches on the ground will actually move forwards and rearwards. So the center line of that front axle will often change its location. So I'll be using an ISO coordinate system with an origin along the center line of the car on the ground and aligned with the rear axle. One thing you'll note if we go into a SolidWorks model is that by default, SolidWorks will have Y as the vertical coordinate. Now we can change that by going into the view properties and turning that to a Z on the up axis, and it relocates all of the different views. Then we should go through and rename those planes, especially of the main CAD model assembly. When we're modeling parts, it's pretty important to use those origins of the individual part files and the planes of the original part files in a really sensible way so that they would align with clear mating faces or centers of geometry. And that really brings me to the last point that I wanted to make in that video, and that is, how do we actually organize the model itself, or the main assembly? So in a vehicle assembly, you'll have the main assembly and then a variety of sub-assemblies, and from those we can have further sub-assemblies, and at the bottom level we have parts. And sometimes it's difficult to know what sub-assemblies belong where. Often we're dealing with connections between those assemblies. A good example of this would be that we would have our suspension that would include our outboard brakes, and then in on the chassis of the car we'll have the brake pedal and the master cylinders, and between those there's going to be brake lines. It can be quite frustrating at times to determine where you want your major assemblies and sub-assemblies to sit in a model. If we organize it well, then it allows us to just open up the sub-assemblies and work on only part of the model and keep the software running a lot faster and a lot more efficient. And one of the ways that I think I like to work on a car model is to roughly break it up based on the major assemblies that will move relative to each other. If we were using this as a lumped mass model in a vehicle dynamic simulation, we would be splitting that up into the unsprung masses, and these would be the corners, so the front left, front right, rear left, and rear right unsprung masses, and then the sprung mass, which would be the chassis, powertrain, and all of the bodywork. If we do it that way in the model, then we can have in our SolidWorks model something that is able to move around. We should be able to move around the sprung masses into various locations and see how the suspension will move as a result of that. Or conversely, it allows us in that top level assembly to move our unsprung masses independent of our chassis and powertrain and move it through the full motion, so the full vertical motions and full steering motions, and we can check for things like clashes of geometry. So that's the way I'm going to organize this model. The main assembly is going to have the sprung mass. So I'm going to actually break that up into two major assemblies. One will be the chassis and powertrain, and the other one is going to be the bodywork and lighting. Now, the reason I'm going to split that bodywork and lighting up is that I've found that it's actually quite difficult to create that bodywork model. SolidWorks is a very powerful package, but it's not the easiest software to use when you are doing surface modeling. So I'm going to want to make sure that I can open up that bodywork and the headlights and everything as a separate assembly and really just work on that remotely from the main model. I'm also expecting that because the bodywork is so crucial to the overall design, that I'm going to be probably doing more geometry iterations on the bodywork than just about anything else on the car. Now the other part, the chassis and powertrain, which we'll be using as the sprung mass, that's going to include the chassis structure, the engine, cooling system, exhaust, fuel system, transmission, electrical, steering, interior, HVAC, and driver controls. Each of those is going to have a major assembly in itself. We want to be able to turn these on and off in our model independently, especially as we're looking forwards and we may consider alterations to the vehicle. So say we want to install a different engine model, we want to be able to just replace that assembly by itself. For each of the unsprung masses, so we'd be looking at the front left, front right, rear left, and the rear right unsprung masses. They're going to include the suspensions for each of those corners, the wheel and tire, and the brakes. As we go along with this model, some of this organization may change, but I'm hoping that the majority of those changes will be in the subsystem level rather than that major assembly. I find it's often very handy to have that main assembly really be a collection of maybe 6 to 10 main sub-assemblies. As soon as you're getting to the point where you're scrolling through the tree on the left-hand side of SolidWorks to try and find parts, you can end up losing a lot of time very quickly. Now, I understand that the content of this video isn't necessarily the most exciting stuff that we do when we're designing. Often we love to get into the CAD and do the calculations and see a lot of the pretty pictures and things like that, and organization and document control isn't the sort of thing that you're likely to be overly interested in. And this is where it'd be silly of me not to note the obvious, is that I'm not Lotus. I'm only one engineer working on the bulk of this, and there are going to be some limitations to how well this can be implemented. I'm going to have to find ways to speed this process up. Now that's going to mean that I'm not going to model every last detail of the car. There are some things where I'm just going to go, yep, as soon as it's at that point, it's okay, I can go ahead and manufacture it. That might mean, for example, not putting every last feature of a purchase part and modeling those purchase parts relatively roughly to make sure that I've only got what I need and no more. In some places, it might be leaving out fasteners or small details. For just about any project, there ends up being a difference between what has been modeled and what ends up getting built. But I do know from experience that the longer I can stay organized in this process, the longer I can stay and make sure that part numbering is kept up to date, the longer I can keep the model in a good, usable and modifiable state, the quicker the project will go. Now, I'm super keen to hear different ways that you may have done your own modeling of your projects and tips and tricks that I may have missed out on. I'm always keen to learn what different methods are out there. So please feel free to put something down in the comments. I've really enjoyed reading what's been put there so far. Thanks for your time.